Ever wanted to get inside an examiner's head? Well, that's exactly what we're doing in this masterclass. We're taking one big, meaty question from a real GCSE paper, and we're going to break it down mark by mark using the official answers. Let's figure out what it really takes to get full marks.
So, here's our game plan. First, we'll look at the question itself. Then, we'll work through all 6 parts. We're talking everything from basic definitions all the way to a pretty tough calculation. And finally, we'll wrap it all up to really understand that examiner's mindset. Let's get to it. All right, the question we're putting under the microscope is question 9. It's from the AQA GCSE Chemistry Higher Tier paper from June 2023. This isn't just one question, it's a whole series of tasks designed to test a bunch of different skills. Let's dive into the first part.
Okay, part 1. 2 marks are up for grabs. We've got the equation for extracting iron. Fe2O3 plus 3C gives you 2Fe plus 3CO. The question asks 2 things: which substance gets reduced and why? But here's the key part: answer in terms of oxygen. That last bit, that's a massive clue from the examiner.
So, how do you make sure you lock in both of those marks? It all comes down to being precise. Let's look at the answer word for word from the mark scheme. And there it is, simple as that. You get 1 mark for just identifying the iron 3 oxide, Fe2O3. The second mark, which depends on you getting the first one right, is for stating that it loses oxygen. See why that clue was so important? If you started talking about electrons, even though you're not technically wrong in the grand scheme of chemistry, you'd get 0 marks for the reason. The examiner wants to see if you can follow instructions to the letter. Okay, on to the next 3 parts. These are quick-fire 1-mark questions. They might look simple, but they're testing some really fundamental knowledge, stuff like mole ratios and reactivity that you've just got to know. Right, question 9.2 is all about ratios. If you look at the balanced equation, you see that 3 moles of carbon make 2 moles of iron. But, and this is the important bit, the question only asks about 1 mole of iron, so we've got to tweak that ratio. The answer is 3/2 times 12G. The logic is pretty straightforward. The ratio of carbon to iron is 3 to 2. So for every 1 mole of iron, you need 3 divided by 2 moles of carbon, which is 1.5. Then you just multiply that by the atomic mass of carbon, which is 12. And that's it. 1 mark in the bag. Now for 9.3. This is about displacement reactions, but it's framed in terms of redox, the movement of electrons. You've got a more reactive metal, A, kicking a less reactive metal, B, out of its solution. So what's actually happening on the atomic level? The correct answer is that metal A loses electrons and the ion, B+, gains electrons. This is the absolute heart of a displacement reaction. The more reactive metal A is the generous one. It gives away its electrons getting oxidized. The ion of the less reactive metal, B+, takes those electrons and becomes a neutral metal atom. It gets reduced. And the last of our quick questions, 9.4. For this one, you're given a little table showing the results of some experiments with 4 metals, A, B, C, and D. Your job is to look at that data and figure out which one is the king of the castle, the most reactive of the bunch. And the answer is D. If you look at the data, D is the only metal that successfully displaces all the others from their solutions. That makes it the most powerful, and therefore the most reactive. 1 mark for some sharp detective work. Okay, let's see how they start building on these ideas. Question 9.5 is worth 3 marks, and it connects reactivity with your knowledge of ionic charges and chemical formulas. This is a classic examiner move, linking different topics together to see if you can apply what you know. So you've got 2 jobs here. First, figure out which letter is aluminium. Second, and this is where the other marks are, explain why, using that formula for aluminium nitrate as your key piece of evidence. You need a really structured answer to get all 3 marks. So here's how the mark scheme lays it out, step by step. First mark, just for identifying metal C from the data. Second mark, for stating the critical piece of information that aluminium always forms a 3+ ion. And the third mark ties it all together using the formula they gave you. Since each nitrate ion has a 1- charge, you need 3 of them to perfectly balance out that single 3+ charge on the aluminum ion. It's a beautiful, logical answer. All right, deep breath, here we go. The final part, 9.6. The big one, a 4-mark calculation. This is where a lot of people can start to feel the pressure, but really, it's just another puzzle. This one is on atom economy, and they make it a bit tougher by making you work backwards. So let's break this puzzle down. They tell us the atom economy for the good stuff we want, metal X, is 77.3%. They also tell us the waste product is water. Our mission is to use these clues to work backwards and find the relative atomic mass of this mystery metal X. Let's walk through it. Now, the mark scheme actually gives a couple of ways to solve this, but we're going to take what I think is the most direct route. First, we'll figure out the mass of all the waste and what percentage of the total that is. Then we'll use that to scale up and find the total mass of everything involved. Finally, we'll just subtract the waste to find our answer. First things first, let's look at the waste. The equation shows we make 3 moles of water. Since the MR of one water molecule is 18, the total mass of our waste is 3 times 18, which is 54. Okay, now for its percentage. If our desired product, metal X, makes up 77.3% of the mass, then the waste has to be what's left over. So 100 minus 77.3 gives us 22.7%. That's our first mark. Easy enough? Now for step 2, finding the grand total mass. We know that a mass of 54 represents 22.7% of the total. So, to find the full 100%, we can divide 54 by 22.7 to find what 1% is, and then multiply that by 100. That gives us a total MR of about 238. And that's 2 more marks in the bag. Nice. And here's the final, really satisfying step. Thanks to the law of conservation of mass, we know the total mass of the things we start with has to equal the total mass of the things we end up with. So if the total is 238 and the wastewater is 54, our desired metal X has to be whatever is left. 238 minus 54 gives us 184. And there it is, our final answer and our 4th mark. Okay, so let's zoom out. We've just spent all this time picking apart one single 12-mark question. What does that actually tell us about what examiners are looking for? What skills do you really need to have sharpened for your exam? Just think about the sheer range of skills they tested in that one question. It wasn't just about knowing a definition. You had to read an equation, analyze data, connect ionic charges to formulas, and work your way through a tricky multi-step calculation. It goes to show that getting the top marks isn't just about memorizing facts. It's about being able to connect those facts and apply them, often under pressure. When you boil it all down, this whole masterclass comes back to one single word: precision. It's about answering the exact question they ask. It's about showing you're working clearly. It's about building your answer step by logical step. So the real question to ask yourself now is, how can you bring that level of precision to every single answer you write? Because that is the key to thinking like an examiner.